Hello and a very good day. For this video presentation, we would like to discuss on the task given for the subject of power system analysis and protection. And our project title is Simulating Power System Response at bus 50 and 51. For the introduction, for our group, the type of disturbance that we have obtained is a non-bolted three-phase fault at bus 50 and 51. It is quite common to consider the power system as operating on balanced condition because a balanced power system must fulfill the following requirements, which is three-phase balanced voltage source, three-phase symmetrical load, three-phase transpose feeders, and three-phase equal self-impedance. For the objective of this project is to model a test system model of power system using MATLAB to analyze the dynamic response of the system with at the selected bus, to analyze power system fault based on balanced fault technique with a selected clearing fault time. For the scope of this project, modeling of the power system will be produced by using MATLAB. The simulation model is modeled for transient stability analysis of the system. The fault location is at bus 50 and 51 only. For the literature review, MATLAB is an appropriate programming language that was developed by MathWorks, and it allows metric manipulate, plotting of function and data, implementation of algorithm, creation of user interface, which is written in other language including C and C++. For the power system stability, the term power system stability is utmost importance in this field because it is used to define the ability of the system to bring back its operation to steady-state condition. The steady-state stability defined as the ability of the system to bring itself back to its stable configuration following a small disturbance in the network. For the transient stability, it is the ability of the system to reach a stable condition following a large disturbance in the network condition. In all cases related to large changes in the system like sudden application or removal of the load, switching operation, line fault, or loss due to excitation of transient stability. And the dynamic stability is also denotes the artificial stability given to an inherently unstable system by automatically controlled. For the methodology, this is the system flowchart which we start our study on theory for the power system stability. We choose the location of fault at bus 50 and 51. Then we apply the changes of clearing time value according to all three cases for voltage magnitude, rotor speed, and rotor angle. Then we check for the system stability. If the stability is achieved, we will continue to make analysis on the result and also the conclusion. If no, we will go back to the previous method, which is changing the clearing time until the system stability is achieved. For the stable system, we got the duration of time from 1.34 seconds to 1.35 seconds. And this is the graph that we obtained. This is the voltage magnitude for bus 50 during stable state. And this is the rotor speed for the generators. And this is the rotor angle for all the 50 generators. Both graphs are in stable conditions. And next is for critically stable, which is the duration of clearing time is from 1.90 second to 1.91 second. For the voltage magnitude graph, the voltage magnitude at the fault bus sagging down as the time increases. As you can see, the line graph sagging down as the time is increasing. For the rotor speed, as you can see, the peak value for this response increases compared to the previous stable case. And also the same thing happens for the rotor angle, which These both peak to peak values are increasing as the time increases, which shows that the system did not settle down to a new equilibrium point that implies the system is at critical stable state. Next is for the unstable system, which the duration time that we obtain is around 1.91 second to 1.92 second, and the resulted graph is as shown here. The line response for the voltage magnitude is totally not in shape as it is in unstable condition, and the rotor speed peak value, as can be seen here, hikes up after 7 seconds in an unstable condition caused by the unusual acceleration. For the rotor angle, it is also shows the increasing in angle for the generators after 7 seconds, and this could cause a severe damage to the system if it continues for much longer time in real practice. And as in conclusion, we have done some of simulation for the dynamic response for the following disturbance in the system. The transient stability in power system referred as the ability of a synchronous power system to return to stable condition and maintain its synchronism. And third, we need to clear the fault after 1.91 second, which is commonly starting from 1.91 to 1.92, for us to prevent any damage to the system. And that's all from us. Thank you.
I let it fall.